So the vector equation of the line is going to help us not only do stuff we used to know how to do in equations of lines in 2 dimensions, but it'll also help us with working with equations of lines in 3 dimensions. So a little recap about what you already know about equations of lines. You know about y equals mx plus b. It's a straight line in 2 dimensions. The b is your y-intercept, and your m was the slope. And that equation found every single point on that line. Well, when we go to vectors, instead of thinking about points on the line, we're going to think about every point on the line is a position vector to get to that point. So if I took this point R, there's a position vector R that gets me to that point. And if I have another point on the line here at C, there's a position vector that gets me to C. The idea of the vector equation of the line is if you find one point or one position vector that's on that line, and you know what direction the line is going, in other words, in this situation, can you see that the vector AC is a vector on that line? It's the direction that line goes. If you have a point on the line, 2 dimensions or 3 dimensions, and you know the direction the line is going, you can find any other point or any other position vector on that line by getting to the line and then going in the direction any multiple of that direction vector. And it comes out to look like this. Any point or any position vector R can be found by having any vector to start with on the line, vector A, plus t, where t is some scalar, some number, multiplied by the direction vector. So for example, if my line is here and I pick a random point right here, that point's on my line. How could I get there? Well, I could get to that point by first going to A, and then going in the direction of AC, a certain proportion of it. In this case, it looks like I went about 2/3 or 3/4 of the way. And then I find another point. And you could do this with any placement on the line. So we have the vector equation of the line. Anytime you have a vector equation line, this is in 2 dimensions. Your point on the line, x comma y, always is your starting point, a1, a2, plus some scalar times the direction your thing is going. You could look at the x coordinates on their own and the y coordinates on their own. This is called the parametric point. We could also take both that parametric forms and get the t by itself and make the one equation equal the other equation. And this is called the Cartesian form, which if you decide to rearrange it, is just y equals mx plus b. Which is kind of cool. So we're going to find vector equations of a line, and we're going to also sometimes think we could do this one quite easily with y equals mx plus b, because in this case, you would have the point 2, 5. There we go, 2, 5. And it's parallel to the vector 3i minus 4j. So 3i minus 4j, that's 3 minus 4. If we drew that as a vector, that would be 3 to the right and 4 down. Well, could you go from this point and go 1, 2, 3 over and 1, 2, 3, 4 down and find a second point? Absolutely. And if you thought back to grade 10 math, if you had 2 points, you could find the slope. And you could either use a point slope form or y equals mx plus b to find b, and you'd be able to tell me what that equation of that line is. The vector equation of line is less restrictive though. Okay, all you need is, we should draw arrows over these are vectors. You need a starting vector. We have 2, 5. That is its position vector right here in purple. That's the vector 2, 5. And then we know the direction that it's going, 3, negative 4, and you could find any other point on the line by just going in that direction for however short or however long you'd like, forward or backwards. So there's your vector equation of the line. It doesn't need very much information at all. Whereas your old y equals mx plus b, you have to find more information for that. We could write the parametric equations for this. So just look at the x coordinates on their own, the y coordinates on their own. And then we could solve for t and get the Cartesian form. And that Cartesian form is just your y equals mx plus b rearranged. So if we're comparing the two, the vector equation of line, a key thing of that is the vector b, the direction vector. The direction vector is very similar to the slope of your regular equation of line. But unlike y equals mx plus b, the vector equation just needs any random position vector on the line to start. Doesn't matter which one. So if you rearrange these, right, that would have been your equation of y equals mx plus b. Here, in the blue, I just cross multiplied to solve for y. And here, I used grade 10 math in black. If I knew my slope was negative 4/3 and went through the point 2, 5, I could use my point slope and rearrange it to y equals mx plus b and get the same equation. Say awesomeness. Do you have Tracy? So find the equation of the line passing through a point and perpendicular to this vector, right? Perpendicular means negative reciprocal. So again, all we need is, add an arrow over this. Any vector on that line would be a point on the line, or that position vector. And then if this is 3i, perpendicular would flip, and one of them would be negative. Doesn't matter if you put the negative on the bottom or the negative on the top. And that's your direction vector. Parametric equations, just looking at your x coordinates. And the Cartesian one is where you solve for t, and then make them equal to each other. So you had questions like this back in grade 10, where just find the equation of the line passing through 2 points. Now we're going to find the vector equation of the line passing through those 2 points. So what do we need? We're going to need find the vector equation line, we need a point on the line. We have two of them. So for vector A, you could choose either the 1, 4 or the 5, 8. We're also going to need the direction vector. So remember, if you have point A, which is 1, 4, and you have vector B, which is 5, 8, and these are, maybe I'll write these as, I wrote them as points, I'll write them as vectors. There we go. This is your direction vector from A to B or from B to A. How would you get that? Right, here's your origin. If I wanted to go from A to B, I could go back to the origin, which would be negative of this one, and then go from the origin to B, which would be plus this one. So A to B would just be B minus A, which is 4, 4. So now you can write your equation of your vector. And it wouldn't matter if you had 4, 4, or 1, 1, or negative 4, negative 4, or 2, 2. They're all the same, right? Because if you think of 4, 4, what's that slope? That's 4 over 4, which is just 1. So any direction vector that would go in that direction, any multiple of it, is fine, because that's what this scalar in front does. So it really, you have lots of options. So now that we've got that equation, we can write the parametric, just looking at the x-coordinate stuff, and our Cartesian by getting the t by itself and making the two equal to each other. Now, it's great that we did stuff in 2 dimensions. I hope you feel that the vector equation is really quite easy, but it's hard to convince you to go away from y equals mx plus b because you're actually pretty good at y equals mx plus b. But in 3 dimensions, this is where vectors are really powerful. Because you don't have a really good equation in 3 dimensions for a line, do you? I don't think we've ever learned that. It would have a y, an x, and a z. Do you have an equation that comes to your mind for a straight line in 3 dimensions? No. So we have a problem. However, it's just as simple in 3 dimensions as it is in 2 dimensions for the vector equation line. You just have any point that you start with. So it goes through 1, 5, 3, also goes through 2, 0, negative 4. You could use either one of those for A. The direction vector, well, if you go from P to Q, that's just Q minus P. Again, if you ever forget how to find that, I like to write it this way because I can visualize. If I started at Q and I was only allowed to travel along the vectors that I knew, I would have to go back to the origin, that's negative Q, and then go to P. That would be like going from Q to P, origin. For solving, it's easier to write Q minus P for doing the math. For thinking about it, it's easier to visualize negative Q. Oh, that was QP. Right, negative Q plus P. PQ would be negative P plus Q. Easier to visualize if you do the negative part first. So we get an equation of line, and now we can answer questions like, hey, would you go through this point? Negative 1, 3, and 5. So the answer is, if you would go through that point, -1, 3, and 5, it would make this equation true. In other words, is there a t, a time, that's why they often use t here, because it often represents time. Is there a value of t that would make this true? Well, if we look at the three parametric equations, the first equation, t would have to be -2. The second equation would work if t was 2/5. And the third equation would work if t was -2/7. In other words, no. In order for it to be on the line, you would have to get there with the same t value each and every time. What about this point? Well, this probably says no. What about this point? So we look at each one. Oh, this is very anti-teacher-like. Sorry for being anti-teacher-like. Usually, if example A was an example that doesn't work, doesn't the teacher usually give an example B that works? But example B looked like it was going to work. But then at the very end, the t-value was wrong and not the same. So the only way a point would be on the line is if there exists some scalar that you could go on that direction and get to that point. But that scalar can't be different for the last value. So then sometimes they give you the same equation line in some weird forms, which we see in this next example. The vector equation line is given by, I'll add an arrowhead over top of that r, 3 plus 2t and 5 minus 5t. You see they sort of made a vector with the parametric equations? Could you rewrite this like this? No problem. Do you remember what a unit vector was?
One over the determinant times the original.
That's how to find it, but what is, yes, and what does it make it? It makes it a vector with a length of 1 in the same direction as your original one. So a unit vector has a length of 1, and yes, you find it by first finding the length of b, because this is the direction vector, so we have to look at b. Its length is square root of 29, and you could either write it like this. I don't mind. I probably prefer writing it like that. Looks cleaner. If the length of b is root 29, if you just divided that length by root 29, you would get a length of 1. And so that makes it the unit vector. And then it asks for the Cartesian form. Well, the Cartesian form says take your parametric forms, solve for t, and make the two parts equal. And that's your regular Cartesian form of the line. Go back for a second, yes, to this one. This one that we just did, would it make sense that the parametric of this would have 3 different equations? You'd have x would be 1 plus t, y would be 5 minus 5t, and z would equal 3 minus 7t. These would be in 3 dimensions, the parametric equations in 3 dimensions. So the equation of a line in 3 dimensions, the Cartesian form, actually looks like this. Could you get t by itself? Yes. X minus 1. Could you get t by itself here? Yes. You would have y minus 5 divided by minus 5. And could you get t by itself in this one? Yes. It would be z plus 3, no, sorry, z minus 3 over negative 7. And all 3 of those would be equal to each other. So you sort of have a system of 3 equations with 3 unknowns, because it could be these 2 equations are equal, these 2 equations are equal, and the outside ones are equal. That's like 3 equations with 3 unknowns. And any point that satisfies all 3 equations would be a point on that line. But it's kind of awkward because now there's 2 equal signs, and that looks like it's not very much fun to work with mathematically. All right, 2 lines, L and M, have vector equations. So we have vector equation R with a little sub L, and vector equation R with a little sub M. And these are bolded, but if you're doing them in your notes, those would all have arrows over. Every vector you have to draw an arrowhead over. So the first thing I would do with these ones is I don't like that form of that equation. I would change it to this one. See, the common point is 5, 3, and 0. And then S is your scalar that gets multiplied, and you're multiplying by -4, then you're multiplying by 1, and then here you're multiplying by 2. Same thing with the second equation. The point is -3, 7, and 6. And the t-value has a -4, a -1, and a 0. So for visualizing things, here we have 2 lines in 3 dimensions. And apparently they cross at one point. How do we find that common point? Well, we look at the parametric equations for the one line and the parametric equations for the other line. You get actually a whole bunch of little mini systems of equations. Now, unfortunately for this systems of equations question, it's too easy. But for example, could you see that if the x's are going to be the same, then 5 minus 4s would have to equal -3 minus 4t. But that wouldn't be enough to solve anything because you don't know s and you don't know t and you just have one equation. But if I look at my y's, this now means that 3 plus s has to equal 7 minus t. That gives you another equation with s and t. And after just the x and the y, you would have 2 equations with 2 unknowns, which you could solve. However, this one is an easier question because if they had a point in common, based on this, does it not have to be that z has to be 6? So if z has to be 6, the only possibility is that s has to be 3. And if s has to be 3 and you plug that in for the rest of it, you could solve for t. But you have to be careful that you check if it works all the way through. So we can solve for s equals 3. Based on that, y would have to be 6, and x would have to be -7. Does it actually work? Is there a t value that does this. Can you see that if you want x to be -7, then t would have to be 1? And if t is 1, is y 6? And of course z is still 8. These questions, when you're finding a common point, you have to check them, because sometimes it works on one equation, it looks like everything's fine, but you plug it into the other equation and it's like mostly worked, but not completely worked. In fact, in 3 dimensions, it is much more likely that 2 lines never cross. There's lots of lines that never cross in 3 dimensions. This is strategic, because airplanes fly lines, and it's a very good thing that they don't share the same point at the same time very often. It's disastrous when they do. Does anybody know the name of the job of the person that makes sure that planes don't cross?
Air traffic control?
Air traffic control. And now we have 2 lines, and these 2 lines happen to intersect. So when 2 lines intersect, there's going to be an angle between them. And so you have to kind of imagine that you could figure out which plane that you could look in where they intersect, where both lines are in, and then find the angle in between them. And again, this is going to be not very hard using vector equations of lines. Okay? Here's our 2 equations of lines. We already determined that they intersected. If they didn't intersect, there's no angle between them, because they never intersect. So first of all, in order to find the angle between them, the 2 have to intersect to begin with. Once we've determined, which we did, that they do intersect, if you want to find the angle in between them, that's where we're going to use our dot product. And we're going to use the dot product with the 2 direction vectors, because this line in green, it's going off in this direction, and this line in blue is going off in this direction. We are trying to find the angle in between them. And we determined that they did share a point in the previous question. So, to find an angle between direction vectors, here's my one direction vector, here's my other direction vector, and then we can use our formula from the dot product. That cos of theta is u dot v, I have my arrowheads on here, over the length of u, length of v, and we get 15 over root 21, root 17, we can do cos inverse, and we get 37.5 degrees. Or if your calculator was in radians, 0.654 radians. Yes?
Does it say cos of 10?
Does it say cos of 10? No, that is a very ugly theta. This one?
Yeah.
That's a theta. See, it's even like a frowny theta. It's so ugly.